Okay. A car starting from rest accelerates at 2.5 meters per second squared for 12.5 seconds. What is this final speed? Well, since the definition of acceleration is a change in speed or change in velocity per time, Vf minus Vi over t, we know our acceleration, we know our time. This is another one that is given to us in words, and another one that I've had students not appreciate. That means that your initial speed is 0. At this point, your final speed, which is what you're looking for, is Vf. Your initial Vi was 0. It's 12.5 seconds. And your acceleration, this is not free fall. This is a horizontal acceleration. So it's 2.5 meters per second squared. So this gives you a final speed of 31.25 meters per second. And you see me using a non-standard abbreviation for second. So let's look at our significant figures. We have 3 for our time. We have 2 for our acceleration. For our initial speed, since it's at rest, that is really more of a defined value of 0. So you have as many of these as you need. So the smallest, since we're simply doing multiplication, is 2. So this should be a final speed of 31 meters per second. Now if we look at our equations of motion, under constant acceleration, this is simply a rewriting of the definition of acceleration. Acceleration is Vf minus Vi over t. This is the displacement or the distance covered under uniform acceleration, and it can be written two ways. This is looking at an initial and a final position, and this is simply looking at a change in position. It's the same thing. There are a couple of ways to get to this. Algebraically, we can simply think of it as, if we're looking at velocity and time, this is the distance, this is the displacement that it covers. And you can find that by simply the area of a triangle, 1/2 t, and the height, which is v, is going to be an at times at. That's if you start at rest. If you're starting something other than rest, it's the same idea, but now this is your initial speed. Here is your time. So now we have in this term, which is VI t. The third one is actually an algebraic combination of the first two. Essentially what you can do here is you can solve this one for t, substitute t in. Notice this one has no time in it. So now we can algebraically combine these two. You don't strictly need to have this one, but this one is convenient, because if not, oftentimes when time is no longer part of what you've been given, you end up having to work both of these in terms of t and going through this process. So this one is a useful one to have handy. The acceleration due to gravity on the Earth's surface is about 9.81 meters per second squared, and the negative tells you that it's going down. Well, we know typically if we release things, they fall. This is one of those values I do expect you to know or have handy. If a rock is dropped and falls for 2.5 seconds, how far does it go? Well, I'm going to write this in terms of a delta y, 1/2 at squared plus VIT. It's dropped, so VI is 0. Acceleration is acceleration due to gravity. That's a negative 9.81 meters per second squared, and it falls for 2.50 seconds. Solving this, gives you 30.66 meters, and it's a negative because it's going down. Well, if we look at our significant digits, here are 3, here are 3, and since it's dropped, we have this defined to be 0 with as many decimal points as we need. So either way, we have 3, a negative 30.7 meters. And this 0 is significant because it is between two non-zero digits. A car starting from rest accelerates at 2.5 meters per second squared for 12.5 seconds. How far does it go? Well, it's the same situation we had a minute ago with the car, except instead of asking how fast it was at a certain time, I'm asking how far it's going. So delta x is 1/2 at squared plus vi t. Delta x is 1/2 2.5 12.5 squared, and since the initial velocity from rest, vi, is 0, this term becomes 0. So this gives me a change in position of 195 meters. Proper number of significant digits in this case should be 2. So this is where this gets a little bit tricky to handle. In scientific notation, we would do it like this, making that 0 significant. Sometimes you will see it written as a number with a bar on it. In this case, that bar is used to indicate significance. That's one of the ones that's a little bit trickier to deal with, showing proper significant digits. Now we're going to talk about vector notation. Because sometimes it does matter which way you're going, we're going to start bringing in the idea of a vector. A vector is a quantity that shows not only how big something is, but which way it is. Sometimes direction matters. If we're using simple vector notation, the I hat, or frequently I just call it the I, is what we call a unit vector, which means it has a size of 1. That's what unit means, in the plus x direction. And the j, I'm going to write it above, or j hat, is a unit vector in the plus y direction. The k hat, and we won't use it exceedingly so, but we do use it occasionally, is a unit vector in the plus z direction. Now, when vectors are written this way, they're in what we call component form. Component form makes addition very easy because it's just like algebra, collecting your like terms. So I have 3.5 I hat plus 7.2 I hat. And again, frequently I won't say the hat. That just leaves us 10.7 I, 8.1, and a negative 4.6. If I did that correctly in my head, is a positive 3.5 j, or j hat. That's all you have to do for adding or subtracting vectors in component form.